All right, hello AP Statistics students. We're going to continue our investigation of statistical inference today. We've already done confidence intervals for one proportion, so now we're going to look at confidence intervals, hypothesis tests for one proportion. So we're going to start out by investigating this autism problem. And we'll go through a comprehensive process which you should do when you're doing any hypothesis test, regardless of whether it's a one proportion test or something else, something more complex or less complex. Use the same kind of process and it'll guide you. Okay, so it says in the 1980s, people believed that autism affected about 3% of the nation's children. So that's kind of our starting point, our guesstimate for the parameter, or P in this case. Some people believe that there's been an increase in the due to chemicals in autism since then. So a recent study looked at 840 children and they found 30 cases that showed signs of autism. So we want to know, is this new study evidence that the level has indeed increased? So first we want to look at the POI, in other words, the population of interest. So who is the population of interest? Well, in our case, I think it's children of a specific nation. So I'm going to say America's or another nation's children. I guess it depends where we're interested in. It didn't specify up here, so I'm assuming America, but it could be anywhere. The variable of interest in this case is the incident rate of autism. So I think it's really whether or not a child has autism, shows signs of autism. So we're not going to delineate different levels of autism here. It's just they have it or they don't. What do we know? We always want to start by listing kind of what we know. So I think we know how big the sample was in this study. They told us it was 840 children. So we know N. We also, I think, know P hat. So I'm going to go and say P. And you know what? I'm just going to call it P hat instead of writing the symbol in this case. So P hat is 30 out of what, 840. So let's turn that into a percentage with our calculator. So give me a second. And I think I got 0.0357 or 3.57%. So that's what we're seeing. So it's not quite 3%. So the question is that a significant difference or not? You might be saying, no, of course that's not a significant difference. But it depends on the size of the sample, of course, in terms of the mathematical probabilities of how different that is. And so we definitely need to continue our investigation. So what do we want to know? Oh, I think I forgot one other thing we need to list, which is P, the parameter we believe to be 3%, or at least in the past we believed it to be 3%. And we're checking to see if we have a significant difference from that with this new study. All right, so what do we want to know? Well, I think I just said it. We want to know if this new study shows that the proportion, if I can spell right, proportion of autism has changed. If it was just changed and they didn't give us any indication of whether it had gone up or gone down or whether we believed it to have done one of those two things, then it'd be a two-tailed test. Since they use this word up here, increased, I'm going to say specifically whether autism rates have increased or grown. So that's really just a one-tail test. So let's write that down right here. One-tail test indicated. Okay, what are our hypotheses? We've got to put our null hypothesis, in other words, the assumption that nothing has changed. So that's the fact that the parameter has remained at 3%. We'll just assume that. And our alternative hypothesis, since it's a one-tail test, is that the parameter has grown greater than 3%. There's our one tail. We need to decide on a threshold for which we'll reject or not reject a p-value here. So let's see. Is this life or death situation? Yeah, it does involve kind of a medical case, but I don't think anyone's directly going to die as an impact of our test or major huge changes. We're just trying to figure out some information. So I'm going to use the industry standard in statistics of alpha equals 0.05. I really wanted to talk a little bit about another way to actually decide your rejection rule here. This is kind of more old school. Alpha is the way to just use your p-value, which is probabilistic, and kind of the more modern way to go for a variety of reasons that we'll talk about. But another way to actually do the calculation and decide, and interpret your calculation once you're done with it, is to use a z-star threshold. And I think this is good for kind of understanding what a p-value really is and kind of where it comes from. So I wanted to look at the AP tables and develop for the 0.05 level for a one-tail test, what's our z-star threshold cutoff. So here's the t-table that we've seen once or twice now. We're going to get into this a lot more soon. But if we look at the infinity row where we get z-star for our confidence intervals, that's where we'd be getting this z-star for our threshold value as well. The only problem is our test was one tail. These are all two tails because they're for the confidence intervals. And of course, confidence intervals go two ways in two different directions. Remember, a confidence interval is going to go from some center p hat out one way and out another way equally with the margin of error. So we can't use that. So let's go straight to our z-tables, the things we've been looking at for a very long time, and try to pick it from that. So if we've got 5% above, let me just use this little z-star. Well, let me try that again. That's pretty sloppy. Oh, still sloppy. Come on, I can do straighter. I guess not. Okay, so let's get a standard, oh man, a standard bell curve kind of going here. Okay, that's not terrible. So we want a one-tail test, and we want 5% in this upper tail. Let me grab my little tablet I've been experimenting with here. So we want this guy up here to be 5%. So if the table is referring to below, then we need, of course, to look for 95% within it, which I don't see here. I see it down here somewhere. Let's see if we can find it. So let me go back to my drawing tool. 95%, where's the closest thing? I think it's between this one and this one. So that means 1.6, and to be a little more precise, it's between these two up here. Let me get that a little nicer. So it's 1.645. That's our threshold, which will decide whether our results are different enough from 3% or whether we fail to reject. So there we go. So we're going to put, let me go back to my draw and type in here. We're going to say 1.645. There we go. Okay, the procedure is, of course, the only one that we're learning so far. So this is a one proportion, because we're only looking at one proportion at a time, Z procedure, because we're using a z-test statistic. So let's go down here and address our assumptions. So our assumptions, first we need to establish independence. We do that by deciding whether it was randomized. So did they say anything about it being done randomly? They did not, I do not think. So we will assume the sample was collected randomly. Some caution advised. The other thing we need for independence is to make sure we didn't sample more than 10% of the population with our 840. So I'm going to say, yeah, it should be reasonable to assume that there are more children in just about any nation, whether we're looking at America or somewhere else, than 10 times that 8,400. So we're definitely good to go there. So we got a little bit of caution but on the randomization, but hopefully these researchers know something about statistics and collected their sample randomly. The other thing we need to do is check our normality assumption, which is the fact that, I'm just going to insert an equation here, the fact that NP is greater than 10. Is that true? And we also, of course, need to check that NQ is greater than 10. Is that true? NP in this case, let's go back and look at our knowns. We got 840 times P is 3%. That's going to be 25.2. Is that greater than 10? Yep. Good to go there. And then we've got 840 times 97%, which is of course good. But we'll write it down because you need to on the AP exam. If you didn't have these little things here with a nice check mark, it wouldn't count. So our assumptions are mostly safe, except for the randomization is a little bit fishy. So let's go ahead and write down our test statistic in general that we use for 1 proportion z procedures. So for 1 proportion z procedures, we create a z test statistic, surprise, surprise. And that z is of course formed by looking at the statistic, or p hat for us, minus the parameter, or p for us, divided by the standard deviation of that test statistic, which is for us, of course, the square root of pq divided by n. So we just need to divided by n. So we just need to plug in our specific numbers. Our p hat was 0.0357. Our p was just 3%. Or 0.03. And down here, we're just going to put this together and go 0.03 times 0.97 divided by our 840 subjects that we sampled, and put that in our calculator, and we should be good to go. So get a z test statistic of 0.97 approximately, or 0.968 to be a little more precise. 0.97 should be sufficient to go and get my p-value though. So let's go down to our tables and get the p-value for this one. So 0.97, so let's see, z table, so oh, there's the negative, so 0.97. 0.97. So here we go. 0.97 is right here. 0.834. Now the question is, do we want to say 83.4% or 1 minus that? So let's go back up here and think for a second. So where are we thinking about here? Well, what we're really trying to do is think about a picture like this. And here is the middle at 3%, of course, 0.03. And our test statistic, but 0.0357 was somewhere up here. So here's 0.0357. And so are we trying to think about above or below? So you have to think about this. Well, we're trying to see if it's grown. So in other words, we're trying to see if we get with a probability of getting something like that, or even more extreme if this is truly the middle. So I think we're trying to do this calculation up here. So that means that we want the probability, in fact, for our test statistic, that our test statistic z is more than this right here should line up with what we had back up here with our one-tail test above. Okay, so it's the probability that z is more than 0.97, which from our table a second ago we got was 1 minus point, what was it, like 8? I guess we could go back and look one more time because I kind of forgot. I'm sure you did as well. 0.834. That's close. Okay, so 0.834, which is, of course, what is that? 16.6%. Okay, so our p-value is 16.6%. So I think what we want to go do up here is think about our threshold a little more. So our threshold means that since we're at the alpha equals 0.05 level, unless the p-value is more rare, or in other words smaller than 0.05, we're not going to reject. You can clearly see that it's not smaller, so we're going to fail to reject in our conclusion here. You can also, of course, use your z-star threshold to make that decision. So instead of looking at my p-value down here for that, I would look right here at this guy and see if this guy was larger than 1.645. And since, of course, it's not larger than 1.645, in fact, our sample proportion happened 0.97 standard deviations away, not 1.645 standard deviations away, which means it's not all that rare, in other words. This could happen, this kind of sample could happen in a large number of cases, if 3% was actually the number, just due to simple random variation. So let's just write that down conclusively down here and finish up this example. So we conclude that since our p-value is 0.166, and that is not greater, since that's not, which, I'll write it like this, which is not less than what we decided was our critical value, 0.05, we conclude, I'm going to put a little comma here, that we must fail to reject our null hypothesis, or H sub O. There is insufficient evidence to conclude that the incident rate of child autism has increased from 3%. So it's really important that you phrase this the correct way. So it's not that we're accepting the null hypothesis that it actually is 3%. It's just that with this sample, we failed to observe a difference from 3%. It's 16.6% likely that you'd see this difference of what, 0.57% in the incident rate of autism for samples like these. So this is basically due to random variation that we saw such a difference. We definitely don't have enough evidence to conclude that autism has changed, or specifically that it's grown from the time that we established that 3% number. So I hope that you found this example on hypothesis test helpful. We'll look at another one in just a moment.